We will consider the geometric programming problem. This is a special kind of nonlinear programming problem. And the nonlinear programming problem where the objective function of the programming problem and the constraints of that programming problem, these are all in the nature of the polynomial. These are not a polynomial. As we see in many engineering design problems that the objective function which is involved in the nonlinear programming problem, this is in the form of polynomial, not in the form of polynomial. Let me give you one example of that. If there are 3 decision variables are involved, x1, x2, x3, let me consider the function x2, x1, x2, x3 plus x1 divided by x2, x3 plus 3 x2 divided by x1, x2. As we see in this function, the power of x2, x3 in the second term and the power of x1 and x2 in the third term, these are the negative, these are negative power, these have negative powers. Thus, this kind of function we cannot say this is a polynomial. We say this kind of problem as a polynomial. That is why we need to know the definition of the polynomial. Before going to the definition of the polynomial, let me go to the first to the monomial. What do we mean by monomial? Monomial is a single term, say x1 by x2, x3. If I just write down, I can write it down as x1, x2 to the power minus 1, x3 to the power minus 1. This is a monomial. And if we consider the combination of monomials, then that would be a polynomial. Thus, the function I have just mentioned x1, x2, x3, x1, x2 minus x3 minus 3 x2, x1 to the power minus 1, x2 to the power minus 1, this is a polynomial. This is not a polynomial. How to handle in the optimization problem where the objective function or the constraint functions are in the form of polynomial, that part we are dealing in the geometric programming problem. Thus, let me tell you the formal definition of a polynomial. I can say that Cj is the coefficient of the individual monomial, x1 to the power a1j, x2 to the power a2j, thus an xn to the power anj. If we have the individual monomial of the form uj, then we can have the function fx as u1 plus u2, say there are capital N number of terms are there, then this is a polynomial, and these kind of functions are involved in geometric programming problem. Polynomial, this is involved in the geometric programming problem. In more general form, we can write it down in this way: summation j is equal to 1 to n, individual ej's are like that, Cj, and product of n number of decision variables, and I is equal to 1 to n. Here x1, x2, xn, these are all the decision variables. These are generally in the optimization problem we consider the non-negativity constraint, that is the xi greater than equal to 0 for I 1 to n, and here for the polynomial the basic consideration is that aij is real. It could be positive, it could be negative, but we consider in the polynomial Cj as positive coefficients, then only it is polynomial. There is most general kind of polynomials also there, that is called the sinomial, that is not, we are not considering at this stage that kind of functions. Now, we are considering the geometric programming problem where the objective function is in the form of polynomial or the constraints are also in the form of polynomial. Just let me take one example first, then I will go for the general methodology for solving geometric programming problem. Let us consider an unconstant geometric programming problem. That is a function f, we need to minimize the function f, that is of the form 7 x1 x2 minus 1, 3 x2 x3 minus 2 plus 5 x1 minus 3 x2 x3 plus x1 x2 x3. If we just analyze this function, this is a polynomial because the coefficients, as we have said, that the polynomials are of the form of Cj multiplication of the decision variables I is equal to 1 to n, summation j is equal to 1 to capital N. This is the function. The similar function we have considered here. Here capital N, that is the number of terms of 4, small n, that is the number of decision variables, these are 3 here. Now, if this is so, then we can say that this is the first term u1, this is u2, this is u3 and this is u4 for us. Alright. Then as we see for the u1, the coefficients of u1 is c1, coefficients of e2 c2, c3 and c4. These are the coefficients we are considering as 7, 3, 5, 1. And what about the powers? We have the in the first term u1 is equal to c1 x1 to the power a11, x2 to the power a12, x21 rather, x3 to the power a31. Then we have from the first term a11 as 1, a22 as a12 as minus 1 and a21 as a minus 1 and a31 as 1. If I just write down all the informations together, a11, a21, a31, from the second term a12, a22, a32, a13, a23, 24, 14, because these are in the form of aij, I corresponds to the suffix of decision variable, j corresponds to the corresponding term. This is from the fourth term, first coefficient, that is why I is equal to 1, 4 is equal to j is equal to 4 here, 2, 4, a3, 4. If we consider all the coefficients together, we can put a matrix in the matrix notation, a11 as 1, minus 1, 0, 0, 1, minus 2, here minus 3, 1, 1 and the coefficients here 1, 1, 1. Now, this is about the polynomial invert in the objective function. We did not consider the constraint. Now, you can imagine that if we just include the constraint, how complex the problem would be, and it would be difficult to handle the situation. Now, before going to the formal methodology, that is little bit complicated, let me solve this problem first. Now, we will use the differential calculus here because this is an unconstant problem, as we have learned in the classical optimization technique, that is the, if for the minimum, if I want to have the minimum of f, then first we need to differentiate f with respect to the individual decision variables, we will equate to 0. From there we will get the equations and we will get the optimal solutions for x1, x2, x3, and we will ensure the optimal solution is the minimum one by considering the next order derivative, that is the del 2f, and if it is greater than 0 then it is minimum. This is the same process we will apply here. Thus, we will what we will do, we will consider the first order derivative of f with respect to x1. If we consider that as this is the function for us 7 x1 x2, then that would be the corresponding first order derivative plus the second term will be 0, the third term minus 3, 5, x1 to the power minus 4, x2, x3 plus x2, x3. And we will equate this is equal to 0. What about the second? Del f by del x2, if we consider this is equal to minus 7 x 1 x 2 to the power minus 1 plus 3 x 3 minus 2 plus 5 x 1 minus 3 x 3 plus x 1 x 3 equal to 0. Similarly, del f by del x 3 we can have this is 0 because there is no term in the first where x 3 is involved. From the second we have minus 2 3 x 2 x 3 minus 3 plus 5 x 1 minus 3 x 2 plus x 1 x 2. This is equal to 0. As we have seen that we are having 3 equations from here, and one thing you just see, if I just multiply x 1 with del f x 1, then we are getting the function x 2 minus 1 x 1 plus minus 3 rather the next term let me write down in this way 0 into 3 x 2 x 3 minus 1 plus minus 3 5 plus x 1 x 2 x 3 is equal to 0. Similarly, if we just multiply x 2 f x 2, we will see that we will get another form, that would be minus 1 into 7 x 1 x 2 inverse plus minus 2 into 3 x 2 x 3 minus 2 plus 5 x 1 minus 3 x 2 x 3 plus x 1 x 2 x 3 is equal to 0. As we have seen that the functions x I del f by del x I, this is in the form of summation a I j u j, where the terms, this is u 1, this is u 2, this is u 3, this is u 4, and just we have considered the coefficients. Here the coefficient of x 1 is 1, the coefficient of x 1 is 0, coefficient of x 1 is minus 3, coefficient of x 1 here is 1. Similarly, in the next, the coefficient of x 1 is minus 1, coefficient of x 2 is minus 2, in this way. If I just consider, then we will see for individual functions we can just summarize in this way that j is equal to 1 to 4 and x I, we will get these equations. I is equal to 1, 2, 3 here, and this equation is very important for solving our geometric programming problem, because from here we will get one set of equations, from there we will get the optimal solution. Just remember this equation, I am going to the next. Now, we are having the equations like a I j u j is equal to 0, j is equal to 1 to 4. If we just solve this equation, what we will get? We will get x 1 star, x 2 star and x 3 star, and let this optimal solution, this could be the possible optimal solution for the given function, because this we are getting from the differential calculus process, and if this is so, if it provides the objective functional value as f star, then we can just let me simplify this equation further, considering uj divided by f star is equal to 0. If we consider so, then we are getting, there is a meaning of this thing. We can consider this as another variable, say delta j. Then we can say, just look at the simplification process. Why I am doing so, that you will realize very soon, because Thus, what we can say that instead of what we do in the geometric programming problem, instead of solving this Aij uj is equal to 0 summation, this is a little bit complicated equations for us, difficult to solve, difficult to get x1, x2, x3 star directly. We are solving these equations where we are considering delta j's are the decision variables. And from here how many equations we will get? We will get 3 equations. And another fact you just look at, what is our delta 1? Delta 1 is equal to u1 by f star, delta 2 is equal to u2 by f star, delta 3 is similarly, and delta 4 is also the same. Then we see that at the optimal point x1, x2 and x3, at this point delta 1 plus delta 2 plus delta 3 plus delta 4, this is equal to, we have u1 at the optimal level by f star, u2 at the optimal level by f star, u3 at the optimal level, so on and so forth. If we just write it down, then we see that u1 plus u2 plus u3 plus u4, this is at the optimal level. We are considering the individual, the values of the individual terms, rather the polynomial, rather the objective function, where u1 is the first term of the given objective function, u2 is the second term, so on and so forth. This is equal to f star. Then certainly this value is equal to f star, then f star by f star we get this is equal to 1. Then from here we are getting the fact that this is the first set of equations where the decision variables are delta j's, and this decision variables 4 decision variables are there, they were delta 1, delta 2, delta 3, delta 4, and another equation we are getting delta 1 plus delta 2 plus delta 3 plus delta 4 is equal to 1. These two sets of equations, rather 4 equations we will have, and we are having 4 unknowns, and from there very easily we can find out the optimal values for deltas. Instead of finding out the optimal values for xi's, we are finding out the optimal values for delta j's, because in geometric programming we do in that way because this is easier to handle. Thus, let me just write down the next fact, that is we are having 2 sets of equation, as I said, del aij delta j is equal to 0, j is equal to I 1 to 4 and I is equal to 1 to 3, and another set summation delta j again over delta j, j is equal to 1 to 4, this is equal to 1. From here we are getting 4 sets. This is called the orthogonality conditions, and this is called the normality condition. Thus, in the geometric programming problem, whenever we are having any polynomial with us, we need to optimize the polynomial. In that case, first we will formulate the orthogonality condition and the normality condition. Now, look at this matrix. From the same matrix, we can formulate the orthogonality condition. How? We will just multiply 1 into delta 1 plus 0 into delta 2 plus minus 3 into delta 3 plus delta 4 is equal to 0. Minus 1 into delta 1 plus 1 into delta 2 plus delta 3 plus delta 4 is equal to 0. In the similar way, the third orthogonality condition can be formed for the same problem. Thus, we get delta 1 plus 0 into delta 2 as I said, the same thing I am writing here, that we can get from the given, we are constructing the matrix before, from there and we will consider the orthonormality condition, that is delta 1 plus delta 2 plus delta 3 plus delta 4 equal to 1. Thus, we are having 4 equations and 4 unknowns. From here very easily we can calculate the values for delta 1. This is the possible minimum value for delta 1, that can be half, delta 2 star is equal to 1 by 6, delta 3 star is equal to 5 by 24, and delta 4 star is equal to 3 by 24. One thing to be mentioned here, for this problem we are having 4 equations, 3 decision variables, thus we are getting the unique solution for deltas, but this is not happening every time. We may have that capital N, that is the number of terms, these are not matching with the number of decision variables. In that case, unique deltas we will not get. Here there is a concept of degree of difficulty of the geometric programming problem. Whenever we are getting any geometric programming problem, first we need to calculate the degree of difficulty here, that is called the degree of difficulty. If the degree of difficulty is 0, then we will get the unique solution for that geometric programming problem. But if the degree of difficulty is not 0, it is for the negative degree of difficulty it does not work. For the positive degree of difficulty only we can get the solution. Thus, we can have the multiple solutions for the geometric programming problem. How to calculate the degree of difficulty? The calculation is that capital N minus 1. Alright, for this problem as we see the number of terms of 4, number of decision variables 3 and minus 1, this is equal to 0. That is why we are getting unique delta j's. Otherwise, we will not get unique delta j's, our calculations would be little bit difficult. Thus, we need to remember for 0 degree of difficulty we are having unique solution. For non-zero degree of difficulty, that is the positive non-zero degree of difficulty, we will have multiple solutions for the geometric programming problem. And for the negative degree of difficulty, this methodology is not applicable at all. Now, once we are getting delta 1, delta 2, delta 3, delta 4, what is our target? Our target is to find out the objective functional value at the optimal level. Not only that, the decision variables values as well. We do not know these values, we only know the values of deltas, and from here we need to calculate all these 4 values. Now, in geometric programming problem, this is the beauty of this geometric programming problem, is that we do not calculate the decision variable values first, as we do for other nonlinear programming or linear programming problem. We calculate the optimal values of the decision variable first, then we substitute the values in the objective function and we get the optimal value of the objective function. But in the geometric programming problem, we do not do so. We first calculate the objective functional value at the optimal stage, then we will go for these values. One advantage is that in some optimization problem, some decision making problem, really we do not need to calculate the optimal decision variable values, rather we need only the optimal objective functional value. Then we can stop our process there itself, because in the next stage we are going to calculate f star. What are the known things for us? We know delta 1, delta 2, delta 3 and delta 4, these are all known at the optimal stage. From here we will calculate the value of f star. What is the process? Just see. We need to calculate f star. F star can be written in this way, f star to the power 1. Then for this problem very easily we can calculate f star to the power delta 1 plus delta 2 plus delta 3 plus delta 4. Alright. Just now we have considered that delta 1 is equal to u1 divided by f star. Thus, we can say that f star is equal to u1 by delta 1. Similarly, for 2 as well, for 3 and 4, for everything. Thus, we can say f star is equal to u1 by delta 1 is equal to u2 by delta 2 equal to u3 by delta 3 equal to u4 by delta 4. Same fact we are using here. What we will do? We can consider, say, f star to the power delta 1, f star to the power delta 2, f star to the power delta 3, f star to the power delta 4. Thus, after simplification, just we will substitute u1 by delta 1 to the power delta 1, u2 by delta 2 to the power delta 2, u3 but you see we know the values for delta 1, delta 2, delta 3 and delta 4, but we do not know the values for u1, u2, u3, u4. How u1 looks like? u1 looks like for this problem u1 is 7 x1 x2 minus to the power delta 1. Similarly, u2, let me write down in general form c2 x1 to the power a1 2 x2 to the power a1 2 2 x3 to the power a3 2 divided by delta 2. Similarly, okay. Once this is so, let me just simplify this fact. Instead of 7, let me write down C1 for this problem. C1 by delta 1 to the power delta 1, C2 by delta 2 to the power delta 2. We are taking out this C because C1 delta 1, C2 delta 2, these are all known to us. Therefore, we can substitute the values for calculation, but we have another set of terms as well. Let us see how we can simplify that fact. As we see from here, x1 is equal to 1 into delta 1 plus a22 into delta 2 plus a33 into delta 3. In this way, if we just proceed, we are getting that x1 is equal to a1j delta j summation over j, alright. Similarly for x2, similarly for x3. Thus, let me write down in more general form as Cj by delta j to the power delta j. From these 4 terms, j1 is equal to 1 to 4, and from here we are getting for individual xi's summation aij delta j. J is equal to 1 to 4, I is equal to 1 to 3. Just now we got the fact that these are the orthogonality conditions, and we have seen from the orthogonality conditions that summation aij delta j, this is equal to 0. Thus, we get x1 to the power 0, x2 to the power 0, x3 to the power 0, and these are all 1. Thus, we can get that the objective functional optimal value as this value only, because all these terms will converge to the value to 1, alright. This is the way we can calculate the objective functional value. We will just substitute the Cj values C1, C2, C3, C4 for the given problem. These are all 7, 3, 5, 1, and delta value just now we have calculated half, 1 by 6, 5 by 24 and 3 by 25. We will just substitute the values and we will get the objective functional value for f star. Now, for this problem, if we just want to calculate the objective functional value, these are the theories I just have said. Then objective functional value of f star would be 7 divided by delta 1, that is half to the power delta 1, 3 divided by 1 by 6 delta 2 to the power 1 by 6, 5 divided by 5 by 24 to the power delta 4, sorry, this is delta 3, yeah, 1 by delta 4 to the power delta 4, I should not write delta 4, 3 by 24. This value is coming as 761 by 50. Thus, this is the minimum value of the objective function. Just to see the beauty of this process, that we did not to calculate the decision variables at the optimal level, see directly we can get the optimal value of the objective function. That is one advantage for this geometric programming methodology. If we do not need to calculate the other values, do not go, otherwise we need to determine the values xi's. Let me tell you the process, how to calculate x1 star, x2 star, x3 star and x4 stars. As we have seen that u1 at x star divided by f star is equal to delta 1. Thus, we get from this equation that 7 x1 star into x2 star minus 1 is equal to f star, that is 761 by 50, and delta 1 is equal to half. all right. And we are getting another equations as well from other j's, that is the next term 3 x 2 star x 3 star minus 1 is equal to 761 by 50, that is the f star, into delta 2, that is 1 by 6. The next 5 x 1 star minus 3 x 2 star x 3 star is equal to 761 by 50 delta 3, 5 by 24. And the next term 3 by 24. Now, we are having 4 equations and 3 unknowns. Very easily we can calculate the values for x 1 star, x 2 star and x 3 star. But you see, these are again the nonlinear functions. Sometimes you may feel difficulty in calculation in getting the values for x 1, x 2, x 3 very easily from here. There is an alternative process for solving it. The process tells you that just take the logarithm in the both sides. Once you are taking the logarithm in the both side, then what we get? We get, just take 7 this side, then we get log x 1 star minus log x 2 star is equal to some value, say this divided by 7, some value we will get here. Thus, from this set we will get another linear equations, and rather we can say this is in the form of W1 minus W2 is equal to some value, say R1. R1 is equal to 761 by 100, 100 into 7, 700, that is your R1. And from here we are getting W2 minus W3 is equal to R2 minus 3 W1 plus W2 plus W3 is equal to this thing, and W1 plus W2 plus W3 is equal to R4, where Wi is equal to log of xi, rather xi is equal to e to the power Wi. Now, once we are solving these linear equations, from there also we will get the values for Wi's at the optimal level, and once we are getting Wi, xi's can be obtained by considering e to the power Wi. This is the nice fact of geometric programming problem, is that for the convex programming we will get the same fact is also applicable as we have learned before, that is for the convex programming whatever local optimality we are getting, that is the global optimal. Now, the same process let me just explain for the general kind of unconstant geometric programming problem. This is the example I have considered first, so that it can be understood in a better way. Let me consider a general kind of unconstrained geometric programming problem. I am sorry, this is summation, all right, and this is product, because these are all the polynomials Aij, I is equal to 1 to small n. Now, we need to minimize this function xi greater than 0. As we have seen that the process is that we will get del f by del xi equal to 0, and from here we are getting a set of orthogonality conditions Aij uj is equal to 0, j is equal to 1 to n, and I is equal to 1 to small n. And from here we are developing the theory that at minimum f star, these equations can be modified in this way: uj divided by f star is equal to 0. By considering these are all delta j's, we will get the set of orthogonality conditions, that is more important for us. and the normality conditions as summation a I j delta j is equal to 0, j is equal to 1 to capital N. There are smaller number of equations are there, and we are having delta j summation j is equal to 1 to n equal to 1. This is the normality condition. Thus, for any geometric programming problem, first of all, after these considerations, we will just formulate these orthogonality condition and normality condition. Once we are getting that, we can calculate the values for delta j's. Here the thing is that we need to calculate the degree of difficulty. The value is equal to n minus 1. If degree of difficulty is equal to 0, this corresponds to unique solution of the geometric programming problem. Otherwise, we will not get any unique solution for the geometric programming problem. Now, the next task is to calculate the values for f star. As I showed you the calculation, f star can be written as summation delta j's, j is equal to 1 to n, because this value is coming as 1, that is the fact. From here we are getting the calculation in this way: product of capital N number of terms Cj, x1 a1j, x2 a2j, these are the terms j divided by f. F star is delta j, and this is to the power delta j. Why this is so? Because we have the fact that delta j is equal to uj divided by f star, or f star is equal to uj by delta j. In place of uj, we are considering the individual monomials, that is Cj x1 to the power a1j, x2 to the power a2j, xn to the power a1j, nj etc. And from here we can calculate that this can be written as product of j is equal to 1 to n Cj by delta j to the power delta j, and from the individual terms x1 we can have a1j delta j summation j is equal to 1 to capital N. Similarly, for x2 j is equal to 1 to n a2j delta j, and up to xn anj delta j over j. If this is so, these are all from the orthogonality conditions we are getting the values as 0. Thus, in general we can say that this is the optimal value of the objective function Cj by delta j to the power delta j. This is the optimal objective functional value. Then we will go for the calculation for optimal values of the decision variables. As we know that at the optimal level uj star is equal to delta j into f star. From there we can get Cj x1 a1j, x2 a2j, delta j f star. And how many functions, how many equations we will get? That depends on the number of terms. As many terms we have capital N, we will have that number of equations here. These are all nonlinear equations. From there we calculate x star, that is the optimal value, that is the x1 star, x2 star, x3 star. Now, instead of calculation of the instead of going for the nonlinear equations, we can go for the linear equations as well, as I have explained, that go for these w rather 1 a1, a2j w2, anj wn equal to log of delta j f star divided by C j. You can solve these n number of linear equations as well. From there we will get the values for W I, and from here we can calculate the values of x I star. How? That e to the power W I would be the corresponding value for the object, that is the decision variable. If this is so, this is the way we can solve the geometric programming problem, but the solution of the geometric programming problem very much dependent on our well known arithmetic geometric mean inequality. Let us analyze that fact further. Let us see what we are exactly doing in solving geometric programming problem. Are we really minimizing the objective function given to us? Instead of that, we are maximizing the dual of that objective function. That is the fact for geometric programming problem, and whatever I have said, that is totally dependent on the arithmetic geometric inequality. That fact I am going to tell you in the next. That is the how the primal dual relationship is there in the geometric programming problem. See, we know that is the arithmetic mean is greater than equal to the geometric mean. Rather, I can write it down in this fashion. Say these are the delta 1, delta 2, these are all the weights, delta n, y n. Since this is the weights, then therefore we should write. I have used the delta 1 because you see how our deltas are related to this arithmetic geometric mean equality. That is why I have taken these deltas here. Then it says that would be here I should write delta 1 plus delta 2 up to delta n, capital N it should be, because and here we are having y 1 to the power delta 2, y 2 to the power delta 2, y n to the power delta n. This is the arithmetic mean of capital N number of quantities y 1, y 2 to y n, where the weights are we have taken as delta 1, delta 2, del capital N, and this is the geometric mean. And as we know that arithmetic mean is greater than equal to geometric mean, now you see what we can do in the next. Let us consider delta j yj is equal to uj. If this is so, then we can relate our geometric programming problem very easily. We get from here u1 plus u2 up to un divided by delta 1, delta 2, delta n is equal to 1, because we are considering deltas in such a way that summation is equal to 1. That corresponds to our normality condition, as I said before. Then u1, u2, u10 is un is greater than equal to, again this power is 1 here. Thus, we are considering delta 1 y1 is equal to u1. Therefore, we will just substitute here and we will get y1 is equal to u1 by delta 1 to the power delta 1, u2 to the power delta 2. I hope you are getting some relation with our previous methodology now. Now, as we see what is our ui's? Uj's are, as we have considered for the geometric programming problem, Cj and product of xi's aij, where I is equal to 1 to n and we are having j is equal to 1 to capital N. If this is so, from here directly we can write this is our f then, that is equal to u1 plus u2 plus u3 plus un. This is greater than equal to, if we substitute here and if we do the simplification as we did before, that simplification, if I show you once more, that is u1 by delta 1 to the power delta 2, u2 to the power delta by delta 2 to the power delta 2. If this is equal to this fact only, if we just substitute this value here, then we are getting this is equal to multiplication of C j by delta j to the power delta j, sorry, delta j is equal to 1 to capital N. All right. We are minimizing f, that is our target for the minimization problem. What it can be said that instead of minimization of f, what we can do, we are maximizing this function, and this is the beauty is that this is the dual of this function f, and as we know the fact that maximum of the, that is the minimum of the dual is the maximum of the primal. Same fact we can use here, and from here we can establish the primal dual relationship for geometric programming problem in this way. Now, our primal problem is this, we will write down the corresponding dual problem. The methodology I have showed it to you, we are solving the dual instead of primal problem. Our primal problem for the unconstrained geometric programming problem is that summation j is equal to 1 to capital N C j product of x I a I j I is equal to 1 to small n, all right, and we have x I greater than equal to 0. This is our primal, and from here we are getting the corresponding dual. Corresponding dual is maximization of C j, rather let me write down in detail, C 1 by delta 1 to the power delta 1, C 2 by delta 2 to the power delta 2, and C n by delta n to the power delta n. And we have another conditions here subject to summation, these are the orthogonality conditions for us, this is equal to 0, j is equal to 1 to n, and we are having n number of small n number of equations, and we have the normality condition as well, j is equal to 1 to n, all right. What else we have? We have the fact that delta j's are the decision variables for us, these are all greater than 0. Thus, we see that geometric programming problem methodology in such we have developed in such a way that it has been developed in such a way that really we are not concentrating on the primal problem, instead of that we are concentrating on the dual problem, where the dual function we are maximizing subject to these orthogonality conditions and the normality condition, and whatever solutions we are getting, the dj is the optimal solutions, from there whatever objective functional value we are getting from here, that is same as the objective functional minimum objective functional value of the primal problem. That is the beauty of the geometric programming problem. Now, we can extend this idea further for constrained geometric programming problem as well. How to do that? Let us consider a general kind of constrained geometric programming problem. Where we have the objective function as well as we have the constraint of that geometric program as well. Rather, we have the function minimization of f x is equal to summation j is equal to 1 to n C j product of I is equal to 1 to small n x I to the power a I j, all right, and we have the set of constraints, that is j is equal to, let me consider this as n 0, because instead of, let me consider n k minus 1 plus 1, so that it starts from n 0 plus 1, that is n 1, and we will end to n k. That means, we are having say m number of constraints, alright, and the functions, let me consider these are as C0j and A0j, we can consider as Ckj, and I is equal to 1 to n xi to the power Akij less than or greater than equal to 1, and by considering x greater than equal to 0. This kind, how we can handle this kind of constraint geometric programming problem, we can discuss in the next class. Thank you for today.